Qualitatively, we already know that charges with opposite signs attract each other and charges with the same sign repel each other. The goal of this unit will be to determine quantitatively how large is this attraction or repulsion. The experimental result found by Charles-Augustin de Coulomb was that the electric force between 2 point-like charges Q1 and Q2, separated by a mutual distance r, has a magnitude proportional to the product of the charges in absolute value and inversely proportional to the square of the mutual distance r. Through a proportionality constant that is now called the Coulomb constant, that is 8.9910 to the 9th Newton meter square per Coulomb square. And the direction of this force can be manually attributed so that the force is repulsive when Q1 and Q2 have the same sign and attractive when Q1 and Q2 have opposite sign. I'm pretty sure all of you noticed the similarity with the law of universal gravitation from Physics 1. Both forces decrease with 1 over r squared and act along the line joining the centers. The main difference is that gravitation is only attractive because mass can only be positive, and electric force can be attractive or repulsive because charges have 2 possible signs. For example, take 2 charges with opposite sign. The orange charge is attracted by the green charge, and the green charge is attracted back by the orange charge, so the forces look like this. The expression is symmetric because it involves the product of the absolute value of the charges and their mutual distance. The forces are equal and opposite, satisfying Newton's third law. Now, if you look at 2 charges with the same sign, they will repel each other with equal and opposite forces that look like this. Again, these 2 forces will satisfy Newton's third law. You might have noticed that we picked spherical shapes. In fact, a corollary of Coulomb's law is that this law could be applied to any spherical charge distribution. These charges behave as if the distributed charge in the whole sphere was concentrated at one point, the center of the sphere. So what really matters here is the center-to-center distance, r, and that's how we measure the mutual distance. A second corollary is that if the 2 spheres are very far from each other, they would look like points to each other. These point charges are somewhat analogous to point masses you've encountered in Physics 1. What if there are more than 2 charges? Since each pair of charges interacts independently of every other pair, we can use the principle of linear superposition for forces. So if the charge of interest is Q0, then the net force acting on Q0 is the superposition of the forces due to each individual charge. So F1 on 0 plus F2 on 0 plus F3 on 0 plus Fn on 0. This is a vector sum, so we'll work with force components in most practical cases. To begin with, let's just look at a simple example of 3 charges in a line, so a one-dimensional setup. Find the magnitude and direction of the net electric force on the charge at the origin of the x-axis in both cases. Here, a red bead has a 3q charge, a blue bead has a negative q charge, where q is some reference charge value. Let's start with setup A. We will symbolically call u the unit of the x-axis. We label the charges q0, q1, and q2. The net force acting on q0 is the sum of the force of 1 on 0 plus the force of 2 on 0. The force of 1 on 0 is in magnitude equal to k q1, q0 absolute value divided by the square of their mutual distance, which is 2 units. So we get ¾ k q squared over u squared. Let's draw the vector f10. The force of 2 on 0 is in magnitude equal to k q2 q0 in absolute value divided by the square of their mutual distance, which is for u, so we'll get ¾ k q squared over u squared. Let's draw the vector f20. Both f10 and f20 point in the same direction, so f net 0 would be equal to 3/4 kq square over u square plus 3/16 kq square over u square. That is 15/16 kq square over u square. Looking at setup B, Q0 is a negative charge that is now attracted by Q1 and repelled by Q2. So the forces don't have the same direction. We can write F net 0 as F10 plus F20. In magnitude, F10 is 3/4 kq square over u squared. Let's draw the vector F10. In magnitude, F20 will be 1/16 kq square over u square, but this time pointing in the negative x direction. Let's draw the vector F20. So F net 0 is now 3/4 kq square over u squared minus 1/16 kq square over u squared, so 11/16 kq square over u squared. In the next video, you will see a two-dimensional example.